Okay, question 2 is about density, and it'll also be about specific heat capacity later on. So it says, I've got a piece of copper, that's it there. Boom. They want to determine the density of the copper. The student uses a balance to give the mass. So we know Dave's massive verruca. We want to work out the density. They've given us the mass. So the question says, how could they work out the volume? And there's two ways, depending on which way you want to go. There's the easy way on top in terms of the two diagrams. So that one there. I'm going to use the more difficult one because it does come up on exams. So it makes sense for me to model a more tricky one. So the basic idea, get a measuring cylinder on a flat surface. Fill it with water to a certain point. Add the pipe, fully submerge it. Get your new value, subtract those two values. So there's your basic one that you'd have to just word carefully, but I'm going to use the one with the displacement can. And what we know is we're going to get a displacement can, fill it with water on a level surface, let it drain out, then get a measuring cylinder, estimate the size that we want. So estimate the size that's going to be roughly the volume of the copper pipe. And then it's add the copper pipe. So add that, fully submerge it. That's a dodgy copper pipe. Let the water flow through, collect it, and then measure the volume of water. And then here's it without me dodgy scribbles. So estimate the volume and choose an appropriate measuring cylinder. Fill the displacement can with water on a level surface. And you could add in there, let it run through so that no more drips are dripping out. Fully submerge the pipe and collect the displaced water using the measuring cylinder. Measure the volume at eye level to avoid parallax error. And I've done this a few times. This is just the idea that if there's the meniscus for the water, I want my eye level with it, because if I have my eye above or below, it's going to overestimate or underestimate the value, which we don't want. So, and this idea of your eye position and the fact that light is in straight lines, that's called parallax error. Next one, nice question. We've just got to get ready with Dave's massive verruca again. So calculate the density of copper. Remember that we'll use rho as well in your formula sheet. So we can see we want the density. So we know D equals M over V. We're going to check the units. So they want the density in kilograms. Check. They want it in meters cubed. Check. No unit change. So density or rho equals M over V. 0.058 divided by that will give me 8923.1, and the mark scheme says you can round up, so 8.9 times 10 to the 3 or 8,900. There we go. Okay, next one's a lovely question. So a student wants to determine the specific heat capacity of copper, so that's the value C, and we said that that is the amount of thermal energy for 1 kilogram to increase in temperature by 1 degree C. And that's our TE11 that we've used to help us remember it. Okay, so what are they doing? They've got a piece of copper, and we can see that there. They've got a piece of thread attached around it, and we're going to heat it to boiling. So ultimately, what does that mean? That piece of copper is at 100 degrees C. We're then going to remove it using the thread, and then we're going to dunk that into some cold water. It tells us it starts at 20 degrees C. No problem. But what we actually want to then do is find the energy difference. And we can now see the student assumes the thermal energy gained by the water. So that hot piece of copper there, when it's gone in, that thermal energy has gone into the water. So the next part is the water and the copper both reach 22 degrees C. So I don't want that number there. It's gone from 100 degrees to 22 degrees. My delta T, my change in temperature, is 78. Okay, we're happy with that. The cold water gains 1050 joules, no unit change there, and the mass is 0.058, no unit change there either. Fab. So now we're away. So we know Q, M, C, delta T. You can see that they've just used that symbol for change in temperature. And I'm just going to rearrange it from first principles. So we want C on its own, divide both sides by M, gone. Divide both sides by delta T, gone, and we know C equals Q over M delta T. And now we're away. So it's just make sure you can rearrange. And it's always better to be able to rearrange from first principles than it is to use the formula triangles, but they're a nice way of just checking your answer as well. So the change in temperature is that piece of copper pipe was at 100. When we dunked it into the water, it was left at 22 degrees C. trying to catch you out by getting you to use that. Next part then, rearrange the equation, and we've got our energy 1050 divided by the mass multiplied by the temperature change, and then we've got that value there, 232.1. Okay, so the next one is when they did this, their results were lower than the correct value. Two ways this could be improved. So ultimately at this stage here, so I'm going to get rid of all my red doodles now. So at this stage here, we could see, well, when they put the piece of copper in, thermal energy is going to escape from this pot. So insulate the thing and put a lid on. Now, some years, saying insulate it and saying add a lid, they get you 2 different marks, but not in this year. They count as 1 mark point. So the other thing we can have is, well, at the moment, that thermometer is just suspended in there. How do I know the temperature is homogeneous throughout it? And we don't. So really, we should have a little stirrer that we can move up and down to make sure that the temperature is the same throughout the liquid. And there's 2 improvements. So insulate the beaker to prevent thermal energy being dissipated from the system. And the next one, add a stirrer to make sure we've got a uniform temperature, that it is actually at 22 degrees C and it isn't 24 or anything like that. And that's question 2 done.